So we've looked at the Diels-Alder mechanism and we looked at the stereochemistry of the reaction. Now we are going to look at the substituents and how the substituents will affect the rate of reaction. Okay, so in our classic Diels-Alder, we have our diene plus our alkene. We need temperatures of 200 degrees Celsius and high pressure to get this reaction to form cyclohexene. So what we're going to do is we're going to first look at the dienophile to see what we can do to accelerate that rate of reaction. And then we'll look at what we can do to the diene to accelerate the rate of reaction. Okay. So here is our unmodified, just as a reminder, high pressure. Okay. Now, if we put, let me fix my diene. If we put an electron withdrawing group on the dienophile, this reaction will proceed at a lower temperature. Okay, now, if we put an electron donating group on the diene and still have our electron withdrawing group on the dienophile, we can have this reaction proceed at 30 degrees. So, an electron withdrawing group on the dienophile will accelerate the rate of reaction. An electron donating group on a diene will also accelerate the rate of reaction. These substituent effects lower the activation energy for the reaction. Now, when we have substituents, we can also affect the regioselectivity. So if you recall from our stereoselectivity discussion, we're going to retain stereochemistry, and we are going to favor the endo conformation. Now, with regioselectivity, we are looking to figure out where the substituents will go. What region of the molecule? So for example, here we have a diene that has an electron donating group and a dienophile that has an electron withdrawing group, because R groups are alkyl groups and they are electron donating groups, and X equals a halogen, which is an electron withdrawing group. we have two possibilities. They can stay aligned the way they are written, and R and X can be next to each other, or ortho. Or the dienophile can flip, and we get a configuration like this, where R and the halogen are separated by one carbon. This is called a meta arrangement. Now it turns out that the ortho arrangement is the major product, and the meta arrangement is the minor product. And so we're going to look at as why this is the case. Okay, so just to go through this, different arrangements when we have a six-membered ring. Here, R and X are ortho. Here, R and X are meta. And here, R and X are para. So we have a 1-2 relationship, a 1-3 relationship, and a 1-4 relationship. So let's just explore the other case, and then I'll explain why. Again, we have a diene, and instead of having a substituent here, as we did in the last case, which is now over one carbon, we have our dienophile again. Now we can either get the meta product. Okay, you just have to have that 1-3 relationship, or we can get a para product if the diene is flipped. Dienophile is flipped. So then there's a 1-4 relationship there. Again, this is the major product. This is the minor product. So let's explore why this occurs. Okay. This regioselectivity occurs because of the substituent effects on electron density at C1 and C4 of the diene and C5 and C6 of the dienophile. So we're going to look for partial charges. We are going to remember that electron donating groups push electrons away from them, and that electron withdrawing groups are going to pull electrons toward them. So let's take a diene. Okay. When we have an oxygen, such as an alcohol or an ether, these groups are electron donating groups. They can push electrons in. So that lone pair can get pushed into the ring, and then we have to push the electrons out onto the carbon. So that we get a positively charged oxygen and a negative carbon. Then these electrons can be pushed in again, and then we can get a negative charge out on the last carbon. what this means for the diene is that when we have an electron donating group, such as methoxy, at the 1 position, we have a partial negative at C2 and a partial negative at C4 and a partial positive on the oxygen. If we look at a dienophile with an electron withdrawing group, such as an ester where the carbonyl is attached to the alkene. Okay, so this is electron withdrawing. Alright. This is going to pull electrons toward it. I'm going to need a little bit more room than that. What this will equate to is the following for the dienophile. We'll have a partial positive here at C5, a partial positive up here on the carbonyl carbon, and a partial negative on the oxygen. Now let's align these so we can see where we're going to have a partial positive overlap with a partial negative. And this will allow for a bond to form. So if you recall, on our diene, we had a partial negative on C4. And when we align the dienophile in such a way, we can have a partial positive match up. And this will allow for bond formation. If we were to switch the dienophile like this, we would have a partial positive there and a partial minus. So there is no alignment of charge. This is why the meta product is the minor product. And the ortho product is the major product. Now let's look at the case when we have a substituent on C2 of the diene. Here's our diene. And we'll use the same dienophile because we know where the partial positives will be. Let's draw the resonance structures to figure out where the partial positives will be. Remember, methoxy is electron donating. So these are our two resonance structures. So if we do the partial charges, we'll see that we have a partial plus on that oxygen and a partial minus on that carbon. So when we align the dienophile, we want to have the partial positive aligned with the partial negative, and we can see that this leads to a para-substituted product. So this would be the major product, and it's para-substituted. There is a 1:4 relationship between these substituents. All right, now let's look at an example and evaluate which will be the major product. So I have my diene, and it has an electron donating group. I have my dienophile, which has an electron withdrawing group. So let's look at the 4 possible products that we can get from this reaction. Okay, so here is my cyclohexene with the ethoxy substituent. Now, this cyano group, it can be ortho and exo. Sorry, meta and exo, because it's the 1:3 relationship. Or it can be meta and endo. If you remember, exo is when we point in the same direction as the bridge. Endo is opposite. The other 2 possible products will have para-substitution. So this is para and exo. Fix this here. This needs to be an ET. Or para and endo. If you recall, the endo conformation is preferred, and when the substituent is at C2, the charges align to give para-substitution as the major product. So this here would be our major product, where we would be para and endo. Right. This concludes our discussion of Chapter 17, and what we'll work on is doing some NMR and some synthesis reactions using a Diels-Alder reaction.